Electronics class. Okay, so digital electronics. First, let me know if I am audible or not. Is the screen sharing okay? Am I audible? Just write once.
Yes, you are audible.
Yeah, so then it's okay. So then let us start today's session. So digital electronics, as we know, it is common to computer science, electrical, EC, and even instrumentation. So I would like to know how many of you are from computer science over here, electrical, EC, double E, and instrumentation. Anyone from instrumentation? So I know one guy. He told Tathagata he want to appear for this computer science. So what about others? Anyone? So double E. Surya is telling. What about others? EC, ECE, CSE, CS. Okay. Anyone else from instrumentation? Anyone? Okay. So maximum people are from EC. Very good to know. Yeah. So CSE. Okay. So Bhagyashri, am I audible now? Is it okay now at your end? Hopefully I am. That's why you might. I was telling computer science, electrical, EC, and even for instrumentation. As none of you are from instrumentation, so I won't be sharing the syllabus for instrumentation. But you can see digital logic for CS, computer science. This is the smallest part. You can see you have Boolean algebra, combinational and sequential. If you ask what are the important topics, so combinational and sequential circuit, minimization. So this is K-map, number representation, and computer arithmetic, fixed and floating point. So this is very simple. Only a little bit tricky part you can say is this combinational and sequential circuit. Okay, so Boolean algebra is very simple. We all know what is Boolean algebra. Now talking about electrical, guys. So electrical, you have this syllabus mixed with analog electronics. Okay, analog electronics. You can see from this part to this part, this is your digital electronics, and from here to here, it is analog electronics. Okay, so even for electrical, guys, you can say the syllabus is quite small compared to EC or even IN. So if you ask me the weightage, so for CS, I guess somewhere around 6 to 8 mark questions are asked sometimes. Okay, and for electrical, guys, this is also 6 to 8 mark questions each year. So this year I saw there was good questions from digital electronics for EE as well as EC. Computer science paper I haven't seen for this digital logic yet. And for electronics and communication, you can see the syllabus is quite vast and it is intensively written over here. Okay, so same over here also. If you see, this is just one line, it is written that Boolean algebra, but here they have expanded like number system representation, binary, integer, floating point number, then here combinational circuit, Boolean algebra, minimization. So everything here you can see one word has been written, but here they have expanded that one word. Okay, so the only difference you might see is that this semiconductor memories, this is specially for EC. Okay, and this computer organization. So computer organization, it is also there for computer science students. So EC, guys, you are going to read this computer organization with CS people. Okay, so we have branches for CS also. So you are going to study this with CS. I am not going to teach computer organization. Issues till now? Any issues? Okay, fine. So now talking about books and resources. So my main emphasis, okay, while I am teaching, while I am taking a subject, I will say that my notes first. First thing is notes. Why my notes? Because notes that I make, those are actually gist of different books. Okay, those are gist of different books. So I collect notes from books and from different questions also, gate previous year question or even ISRO questions. Those have very good conceptual questions also. So I collect those information from different sources and I compile them for you guys, then I teach for you. Now, if you ask me, sir, anything different, any other resources that we can refer? So first book I will say is RP Jain. So this is a good book. Okay, this is a very good book, very basic, very lucid language, very easy language written. Okay, so this is a very good book. And next book, if you want to read, then you can read this book, Morris Mano. All the books are available digitally also. You can search for PDF, you will get all the PDFs. Okay, and even this book, this is a new book, so you can get a lot of recent information that what are going in the digital field. And this book, it is helpful if you want to pursue your masters in this digital field, okay, VLSI or microelectronics. So this will be very helpful. Why? Because it has lot of examples that are related to real life or recent time problems. Okay, so this book I will suggest if you want to have a very good perspective about digital electronics, so you can read this book. Okay, so next thing you might be asking, sir, from where to practice questions. Okay, questions. So I will say first, for irrespective of the branches, whether you are from EC, electrical, computer science, instrumentation, I will say previous year questions. First, you finish a chapter, immediately you need to solve the previous year questions. Why? Because the previous year questions, those questions are very important. The IIT selecting body, they actually churn out a lot of details from the chapters. Okay, they churn out a lot of details, and those details, if you have understood the chapter properly, then you can apply those concepts in those questions. So my first and most important advice to you people will be to get PYQ's book. Okay, PYQ book. Now you can get any book you want from any coaching centers, or even we will provide you. It's okay. So previous year questions are very important to solve first. Okay, after that you can go for test series or any kind of booklets that you want. You can read those, but first and most important is few important concepts. Okay, so it will be very simple today. I haven't kept anything that is difficult, because first session usually I also used to like that the first class of any topic, it shouldn't be that much difficult. Okay, later on I will load you guys with difficult concepts also. So the most difficult concept in digital circuit, that is going to be your sequential circuits. Most of the students, they face difficulty in this sequential circuit only. They cannot understand what is the concept behind this sequential circuit. And trust me, this year all my students, they were able to solve questions of sequential circuit. I was very happy. Even the questions that were not very much difficult, very much conceptual. Okay, so all the students, they were means they were able to solve the questions of sequential. Okay, so sequential is the most difficult topic in digital electronics. Now let me ask you, what is digital electronics, or what do you mean by digital circuits? Hello, anyone want to say? See, digital, I should have written not digital circuit, I should have simply written circuits. Okay, yeah. So any circuit, okay, any electrical circuit, specifically I should be saying, any electrical circuit, they are of two kinds. I can classify them basically in two parts: analog circuits and digital circuits. Okay, so can anyone tell me what is analog circuit or what is analog signal? What is analog signal? Yeah, the domain of electronics and signals are mostly form of 0 and 1. Those are digital signals. Okay, okay. So analog signal, the simplest form of analog signal is a sine signal. Why sine signal? So analog signals are basically those signals which are defined at every instant of time. See, from this point, from 0 to 1, if I consider this as 1 second, all the instance in between 0 and 1, they are defined, you can see. But in digital circuit, what happens? First of all, okay, can anyone tell me what is a digital circuit? Don't tell me that it is 0 and 1. I am from CSE branch, sir. Okay. Okay, CSE branch. So that is okay. So for computers, okay, I will say it also. Okay, so digital. Don't say me 0 and 1. Sir, digital signals are those signals which are 0 and 1. Don't tell me like that. I need a proper definition or a proper, what means a proper perspective of what you understand by digital signals or digital circuits. What do we mean by digital signals which convert AC to DC? Array, AC to DC, that is what? That is your rectifier, na, Ishita? Rectifier. Now it can be full wave rectifier, half wave rectifier. Yeah. So a digital signal is a time as well as amplitude discretized signal. Okay. Now what do we mean by that? See, this signal, this sine signal, what I can do, so let me copy this in the next page. See, in IGC, we also prepare you for this interview part also, okay? Means if you are studying something, you should know basically why you are studying something, okay? If you don't know that, how are you going to means learn something or understand something? So first step, what we do, hopefully you might have heard, first step is discretization. Now what is discretization? Basically discretization, so I should have taken something else over here. So let me assume that this is 10, okay? 10 will be better. So what is discretization? What do I mean by discretization? Can anyone tell me what is discretization? What do you mean by discretization? The term discretization. See, any analog signal, this is your analog signal, it is continuous in time, continuous in x-axis, which is time, and continuous in y-axis, which is the value of the function or the value of the signal at a particular time instant. Now, discretization means basically that I want to do what? I want to take specific samples of time. I don't want this continuous time, or I don't want the signal to be defined at every instant of time. Rather, I want it defined at some integer values of time, like at 0, at 1 second, at 2 second, at 3 second, at 4 second, at 5 seconds, something like this. So this signal will be 0, then over here means simply, means my diagram is not that proper, but basically what I want specific signals at integer values of time. But still one thing you can note, that this signal, tell me, is it continuous in amplitude domain or in y-axis? Is it continuous in this y-axis? Yes or no? Tell me. So discretization, basically what it does, it simply discretizes or takes samples at a specific time instant, or to be precise, at integer values of time instant, like at 0 second, 1 second, 2 second, 3 second, 4 second, so on and so forth. But you can see, even after discretization, let me assume if this is 10 volt and this is minus 10 volt, so this signal is still continuous in your amplitude. Now next step after discretization is your digitalization. In digitalization, what we do basically, this will be difficult to draw. In digitalization, what we do, we simply discretize your amplitudes also. Like suppose if I say any value, so this is x of n, if x of n at any time instant has a value greater than 5 volt, I will consider it to be as 1. And if x of n at any time instant, if it is less than 5 volt, I will consider it 0. That means what? Here it is 10, let me assume here it is 7, here it is 5. So what I am going to do, this will be 0 at this time instant, as this is 5 volts, so this will correspond to 1. Even here it is 7 volts, so this will also correspond to 1. Here it will be 10 volts, so this will also correspond to 1. So basically digitalization is what? We are discretizing the amplitudes also into 2 levels, or you can even have multiple levels, but the most important or the most widely used convention is what? It is your binary, where we represent using only 2 symbols. Those symbols are 1 and 0. Okay, so binary method basically has 2 symbols. Those are 1 and 0. So up till this point, any doubts? Anyone? Any difficulty in understanding? Let me know. Anything? See, the class should be interactive. Okay, if it is your online class, it shouldn't be like it is not interactive. Okay, so it should be interactive. Okay, so anything you want to ask? Okay, fine. Arya Vashisht, your camera is switched on, so you can just switch it off. Yeah, so that's good. Okay, so now, okay, so one thing I wanted to ask you guys, what does this 1 corresponds to? Not over here. Okay, generally if I ask you, what does this 1 correspond to? And what does this 0 correspond to? What does this 1 and 0 correspond to, if I ask you? Can anyone say what does 1 corresponds to? True, false. Okay, so that is coming, I guess, from computer science background, you can say. Electrical guys, what do you think? 0 corresponds to what? 1 corresponds to what? See, most of you might be thinking, like someone said, Surya said, 0 corresponds to true, 0 corresponds to false. So this is in computer science domain. Or in electrical domain, usually this corresponds to high and this corresponds to low. But this is not generally true. Okay, this is for positive logic, that we assume this, that 1 corresponds to high and 0 corresponds to lower level. What high, what low? High voltage level or low voltage level. Or even some people say that this corresponds to 5 volt, this corresponds to 0 volt. But there is one more logic. Usually we don't follow this logic, that is your negative logic. But in interviews, like for ISRO, they might ask you. So 0 in negative logic, basically 0 corresponds to false, or this corresponds to low voltage level, and 1 corresponds to true. Sorry, this I have written wrong. Zero corresponds to true and 1 corresponds to false, and 0 corresponds to high voltage level and 1 corresponds to low voltage level. So this is what? This is your negative logic. Okay, negative logic representation. So usually we follow this logic system only that most of the times you are going to see 99.9% in all the textbook that we have positive logics only, because this is the most widely used convention in all segments. Okay, so you are going to see this. Okay, so now let me ask you, what is the advantages of digital electronics? Can anyone tell me what are the advantages of digital electronics? Anyone want to say what is the main advantage of digital electronics? Anyone? So you guys should be knowing because you are from final year. So think, stable signal. So from stability of the signal, what do you mean? If I ask you, what does stable signal corresponds to? So very good, that is a very good answer. But others should also know stable signal means in what sense you are telling. Surya. Anyone else? Amplitude of signal remains same. It's not like that. It's not in that sense. See, you have given the answer correctly, but I will say the explanation to that answer is little bit incorrect. Okay, so I will say, so first, as Surya said, stable signal. Now let me explain what does this stability of signal means. See, most of the signal, like I am speaking, okay, I am speaking, so I have this analog voice. Okay, my voice is analog. So what is happening? My voice, it is first going through the mic. Mic is converting my analog voice to what? It is converting it to an electrical signal. So I am speaking, my voice, it passes through a sensor, which is a microphone over here, and it converts it to an equivalent electrical signal. This electrical signal goes to the laptop. Now laptop has specific ADCs, analog to digital converter. Okay, now you might argue, sir, whether we have this ADC in mic also. Yes, you can have this ADC in the mic also, but usually this ADC is there in the laptop. So laptop, what it will do, it will convert this analog signal, this analog electrical signal, to digital signal. Digital signal. Now this digital signal will be transmitted over a channel at your end. Okay, you will receive this, your laptop. So this is transmitter laptop and this is receiver laptop, TX and RX. Now your laptop also has a DAC, digital to analog converter. So this will convert what? This will convert this digital signal to analog signal, and again it will convert to an equivalent electrical signal. And this electrical signal, again same process, there is a sensor which converts this electrical signal to voice signal, or you can say auditory signal, anything you want to say. So this is the whole process. Now by stability of signal, what do we mean? That this digital signal, like some of you guys might be sitting in Bangalore or someplace, Kolkata or in Patna, anywhere you might be sitting. So that is like 1000 kilometer or 2000 kilometer from my place. So what might happen, that when this digital signal is traveling through this channel, there might be noise. Okay, noise. There can be noise due to anything. There can be chattering also, or that there might be electrical interference in your channel. It can be copper wire or optical fiber, anything. It can be anything. So there might be noise. So what happens? This digital signal, they are very stable signal. Why? Because they are least affected by noise. Any one of you have read information and theory coding, ITC? ITC? This might be in your 7th sem or 6th sem, I guess. Information and theory coding. This is only for ECE guys. Anyone? Okay. So that might be in your 6th or 7th semester. So it was there in my 6th semester. So basically everything, that how this digital signal is least affected by noise and all those things, electrical interference or chattering, you are going to read in ITC. Okay, this is the first point that you need to know. Now second important point is what? That storage is easy. Now can anyone tell me why storage will be easy? Why storage is easy? Anyone want to say why storage will be easy? See, storage, let me erase this part. I hope you people have copied this. So yes, one more thing. After each and every class, I send the slides also, okay, in PDF format. I will send it to you on WhatsApp, or we also have our mail IDs. So I will send it to you, okay. So yeah, storage is easy. Now why storage is easy? See, for storing an analog signal, you can see an analog signal is what? It is defined at each and every instant of time. So here I need to do what? I need to say from 0 to 10. So there might be some values infinite, not some, I should be saying. There will be infinite number of values between 0 to 1, or even between 0 to 0.5. There will be infinite number of values. So I need more space to store some analog signal compared to digital signal, where I have the points or the values of the signal at discrete instant of time, and those discrete interval of time, my amplitude is also digitalized. Okay, it is digitalized. That means what? In binary system we only have two levels. Okay, two levels of amplitude. So storage is very easy, or storage, you can say, it will take very less space compared to analog signals. Now the very simple example is that of your CD. So music CDs, if you have seen, okay, music CD, it is something like this, if you people might have heard. So in 90s, 19, like if I want to say 1995 or 1997, first time compact disc came into market, and those were analog things. Okay, analog things. So here you can see only one movie songs were stored, like 8 to 9 songs. 8 to 9 songs, and this was like 723 MB. Okay, then came MP3. So MP3, we had some kind of encoding. I will not go into that. So we used to store what? We used to store like 50 to 60 movies in one compact disc due to encoding. Then came what? Then came DVD. So here we used to compress as with encoding. We did what? Along with encoding, we had compression also. So here we were storing like 100 to 300 movie song depending on the compression level. Then came Blu-ray. Okay, Blu-ray disc. So here we had very high level of compression, encoding, as well as what we had very good quality songs or videos, whatever we had. And now you can see complete thing, means here we had digitalization also. Okay, in Blu-ray. And now we have what? Now we are storing in computers. Okay, so here everything is digital. So you can, in 1 GB, you can store like minimum 5,000 songs you can store. Okay, in 1 GB you can store 5,000 songs. So storage becomes very, very easy. Any doubts, anyone? Yeah, so this is also very good. Digital signal can be encrypted easily. Encrypted. Encryption is very easy. Okay, and stored in memory. Very good. Okay. So now the next important point is fault detection. Suppose when I am speaking, it is not like that the signal is not corrupted by some kind of noise. Okay, obviously it is corrupted, but when it is reaching your end, what is happening, that there is fault detection. Okay, there are various kind of techniques like Hamming code detection, or there are error detector codes. Okay, lot of things there are. So fault detection, it is very simple in digital signals compared to analog signal. Why? Because in analog signal you need to process huge amount of data, whereas in digital signal you don't need to process that much amount of data. Now one more advantage, means there are lot of advantages. One more advantage that I want to say is what? That basically my system speed improves. The system that is basically working on digital system, its speed also improves. Like you can see these days computers, they are very fast. Okay, very fast. So we are using like digital transactions also, you can see. Okay, like your Google Pay, Paytm, everything, it is becoming very easier, very faster, due to everything becoming digitalized. Okay, even your like your fingerprint, your retinal scan, everything is digitally stored someplace in digital locker or with government. So everything is becoming very easy with the help of digital circuits as well as digital signals. Now if I talk about some kind of disadvantage, can anyone tell me what might be the disadvantage? Anyone wants to say? Anyone want to say? Any disadvantage? Any disadvantage? Am I audible properly? Okay, so disadvantage, like I told, all the systems in nature, okay, in nature, anything you take, okay, any natural signals, like your speech signal, everything is analog in nature. Okay, it is analog in nature. Speech signal, or simply humidity, or even your heartbeat, everything is what? Everything is analog in nature. So we cannot exactly replicate, okay, or recreate exact version of this analog signal in your digital. Okay, so there is some discrepancies or there is some error in this. So basically what happens due to this error? So there are few kind of problems that we are going to see. Second problem that we have is your hardware increases. Now why hardware increases? Because every place, as we are processing natural signals, so we need this ADC as well as DAC, because we need to convert one analog signal to digital, because any digital system requires digital input. So for getting digital input, what we require? We require ADC. And then what we do? So simply if I want to draw a block diagram, so any natural signal, if you give input, so first it has to pass through ADC, then it will pass through a system, any digital system, and then again after this completion of process, it will again pass through DAC. DAC means digital to analog converter, and then it will be, we will be getting output. Okay, so usually what happens, hardware increases. Due to increase in hardware, complexity also increases. Okay, complexity also increases. Fine. So these are the few disadvantages that I want to state. Now, application of digital electronics, there are lot of applications. Communication, you can means state n number of applications of digital electronics, like communication, measurement, data processing, control system, digital information storage, anything. So okay, I am not going to state, like image processing. These days lot of you use image processing tools. Okay, so image processing tools, basically any image, okay, any image you take. So you have what, you have pixels. So any pixels, basically they have different brightness, contrast. So by using different filters, you are actually manipulating the values of each of these pixels that you have. Okay, so digital electronics or digital circuits, the most simplest thing is image processing. Like there are a lot of filters, black and white filter, then I don't know, there are numerous filters, means you guys use, even I use, I can't remember the names actually. Okay, so those are what, those are applications of digital signals. Any doubt up to this point, or anything you guys want to ask? Info is lost as many processes are applied to signal info, it's not 100% efficient. Yes, yep, so that is a correct thing. Anything you want to ask? Anyone? Okay, fine. So now, how is a digital system designed, if I ask? So a digital system is basically designed in three parts. First is system design. Second is what? Your logic design. And third is what? Your circuit design. Now, anyone want to explain what are these? Circuit design, system design, logic design. See, I will give you a very simple example. You have a calculator. Okay, calculator you have. So this calculator is what? Basically, you want to design a system that will perform your addition, subtraction, multiplication, division, and there are a lot of functionalities of a calculator. So you want a system that should perform these many operations. So how are you going to implement? You are going to implement them using logic design. Logic design means what? Like simply with the help of and, or, not, XOR, XNOR, NAND, or NOR gates. Okay, so you are going to design these operations with the help of and, or, not, XOR, XNOR, NAND, and NOR gates. Okay, so this is basically what you are going to design this calculator with the help of different gates. Okay, different gates there might be. Okay, now what is this circuit design? Now circuit design basically mean, see this AND gate or this NAND gate, basically they also need to be designed. So how are we going to design this? We are going to design this with the help of diodes, with the help of transistors, okay, or MOSFET, JFET. So those elements we are going to use to design what? To design this internal logic circuits. Okay, so these also we are going to see. ECE guys are going to see this thing. Electrical also, but computer science people, you only need to see this system design and logic design. No circuit design for computer science people. Okay, so basically I should have started with circuit design, that how you actually design an AND gate, NAND gate, XOR gate. But as you people don't know analog electronics and computer science people are also studying with us, So first, very basic, we are going to start with what? We are going to start with logic design. What do we mean by logic design? That means we are going to study different gates, AND gate, OR gate, NOT gate, XOR gate, XNOR gate, gates like all those logic gates we are going to study, okay, in your logic design part. Tell me, any doubts, anyone? Anyone have any doubt? Any doubt? Anyone? So you can ask, means it's okay. Means what is happening? You guys will not be speaking or what? I should be speaking or what? Means there is some kind of hesitation or what? Let me know. You guys shouldn't be shy. Okay. So even I did not know few things when I had started. Okay. When I was studying, I did not know what is Kirchhoff current law, what is Kirchhoff voltage law. It was very difficult for me initially, but then I also studied. My teachers helped me. Okay. So you should always ask whenever you are not able to get something. Okay. So up till this point, this was all about the motivation of digital system. So you people understood? You people understood? Are pixels already existing in digital format or they are little processed to digital format? No. First, your images, basically when you take this image on your mobile phone, there are CMOS. Okay, CMOS. So basically they absorb the brightness of the light and there is image processing going on in your mobiles. Okay, you might see there are various mobile which have less megapixels. Okay, but their image processing is so better, like your iPhone and all. Their image processing software is so better that you get a very crisp quality images. Okay, very crisp images you get. But there are phones like Motorola. Okay, they have 108 megapixel lens, yet the image is not as crisp as iPhone. So basically this processor has the ability, okay, processor. So what basically your processor does, it basically converts your analog signals or analog image to your digital image. That's what you see in your mobile phone or on your computer screen or your TV screen. Okay, so it is converted by your mobile phone. Do you understand? So your lens, it captures analog signals. Okay. Yes. Okay. So first let us study the logic gates. So logic gates, as I told you, basically this is what? Logic designing. So logic gates can be classified in three parts: basic logic gates, special logic gates, and universal logic gates. Now what do we mean by basic logic gates? Basic logic gates can be sub-classified into three more parts. They are what? AND, OR, and NOT. Then we have special gates. Special gates can also be sub-classified into two more parts: XOR gate and XNOR gates. And then we have universal gates. Those are NAND gate and NOR gates. Okay, NAND gate and NOR gate. Now let me ask you, why is basic gate called as basic? Can anyone tell me? Why is a basic gate known as a basic gate? If someone asks you. Anyone? See, with the help of this basic gates, what you can do, you can construct any Boolean logic. Any Boolean logic you can construct using this AND, OR, and NOT gate. Okay, with the help of AND, OR, and NOT, you can construct any Boolean expression. Now, why is a universal gate called as universal? Anyone? Why is universal gate called as universal? See, this AND, OR, and NOT gate I can construct using either only NAND gate. So I have written in small, it is actually incorrect, but it's okay. So I can construct this AND gate, OR gate and NOT gate simply by using only NAND gate or by using NOR gates. So I told you what? That this basic gates, with the help of this basic gate, I can actually construct any Boolean algebra, and with the help of this NAND gate or NOR gate, means taking any one of the following, either NAND or NOR, I can construct AND, OR and NOT. So that is why this is known as universal gate, because only a single kind of gate, it can actually, we can get any kind of Boolean algebra, okay, with the help of this universal gate. So that is why it is known as universal. So if someone asks you, will you be able to answer why basic gates are called basic and why universal gates are called universal? Will you be able to answer, guys? So hopefully, I am hopeful that you will be able to answer. Now, why are special gates called special? That we are going to see, okay, later on, that why they are called special gates. So now let us study one by one. Why is AND? What is AND gate? What is OR gate? What is NOT gate? OR, so XNOR, NAND, and NOT. So first gate is AND gate. So what do we mean by AND gate? I know you people know. So what is AND gate? So this is a 2-input AND gate, okay? Two-input AND gate. So this is the symbol of 2-input AND gate. Anyone want to say anything? क्या हुआ मतलब? कुछ बोलना ही नहीं चाहते हो? You guys don't want to speak? What? We don't know AND gate or what? Come on, you guys know. You are studying from 11th class that what is AND gate. Okay. So AND gate. So AND gate is a gate basically. So if I have to draw the truth table, so I am drawing the universal truth table. See, if A is low, B is low, A is low, B is high, A is high, B is low, and both A, B are high. So an AND gate is a kind of gate which will produce output high. Listen very carefully. An AND gate is a gate which will produce output high when all the inputs are high. So only in this place my output will be high. Rest all the places you can see any one, minimum one of the input is low, or any one of the input is low. Here you can see both the inputs are low, so this will be low. Here A is low, so output will be low. Here B is low, so output will be low. So this is what? This is your universal truth table of your AND gate. So this is basically what? A into B or A dot B. Okay. Now you can model it, or you can simply again redraw this truth table in your positive logic. Okay, in positive logic. So in positive logic, what I told you, that high is considered as 1 and low is considered as 0. Okay, so this will be 0, 0, 0, 1. So this is the basic truth table of your AND gate. Okay, so that now if I want to ask you what is truth table, can anyone define me what is truth table? See, we all study these terms, but usually we ignore. We know what is truth table, but if I ask you what is truth table, you will not be able to answer. So can anyone say what is truth table? And OS multiplication of two different signals means what? And is okay. It's is okay. I understood. Yeah. So okay, what is truth table? So listen very carefully. Truth table is a table which consists of all possible combination of inputs. So what did I say? Truth table is a table which consists of all possible combination of inputs and their corresponding outputs. Okay, so this is the simple definition of truth table. Did we understand? For different sets of inputs, the corresponding output are listed again, the corresponding for the corresponding inputs. Yeah, very good, Piyush, very good. Okay, so this is your truth table. So what did I say? AND gate is a gate where your output will be high when all the inputs are high. So this is a basic what? AND gate. Now let us study OR gate. So OR gate, the symbolic representation of OR gate is something like this. Okay, okay, so I should have told that this is the logical expression. Okay, logical expression that x is equal to a dot b. This is the logical expression of AND gate. Now for OR gate, the logical expression is what? A or B, or you can even, most of the time people say A means A add B. Okay, but usually you should say A or B. In Boolean, plus means OR. So this is what? This is the logical expression for OR gate. Now if I want to draw the universal truth table for OR gate, so OR gate is a gate whose output will be low when both the output or all the outputs are low. So what did I say? OR gate is a gate whose output will be low when all the inputs are low. For AND gate, output will be high when all the inputs are high, and for OR gate, all the means output will be low when all the inputs are low. So you can see at this place only all the inputs are low, so the corresponding output will be low, and rest all the places you can see any one of the input is high, so your output will remain high. Now you can encode this in your positive logic. Usually we see this in textbooks. So this will be 0, 1, 1, 1. Okay. So later on I am going to tell you. So this is what? This is Boolean logic. And in Boolean addition, 1 plus 1, it will be 0 and carry 1. So later on we are going to study this. At the moment you should know in Boolean expression 1 or 1 is always 1. Okay. Any doubts in this? Any doubts? Anyone want to say something? So you guys are leaving or what? Is the class boring or what? What is happening? Are we understanding everything? So this is basically what I said. OR gate is a logic gate whose output is logic high when when all the inputs are, means what did I say? I said logic high. So OR gate is a gate whose output will be logic high when any one of the input is high. And it will be, this is output, and output will be logic low when all the inputs are low. Okay, when all the inputs are low. Okay, so moving on, we have NOT gate. Now what do we mean by NOT gate? Anyone want to say what is a NOT gate? A simple basic representation, or I should be saying a simple means a real life example of NOT gate. Anyone wants to say what is a NOT gate or another name for NOT gate? Anyone? No doubts. Okay, fine, very good. Chalo. See, NOT gate is basically inverter. Okay, inverter you can say, and its logical symbol is something like this. See, I will be dealing a very important concept after this. So if this is A and this is X, so logical expression is A bar. Now what do we mean by bar? This bar corresponds to complement. Okay, if I want to draw the truth table, the universal truth table, so basically A and this will be X. So if A is low or A is high, so output will be just complement. So in binary system we have only two state, high state or low state. So the complement of high will be low and the complement of low will be high. So whenever input is low, output will be high, and whenever input is high, output will be low. So this is the simplest gate you can have. Or if I want to draw it in positive logic, the truth table, so this is A, this is X. So if A is 0, X will be 1. If A is 1, X will be 0. Okay, so this is what, this is basically your truth table for NOT gate. So NOT gate is a logic gate whose output is always complement of the input. Complement also you can say, or you can say opposite, but usually we don't use this term opposite. It is not good to use this term. Now can anyone tell me what is this symbol? What is this? What is this? Amplifier to linear integrate circuit. I am not asking in analog circuit. Can you tell me in digital? In digital? So in digital, this is known as buffer circuit. Now what is this buffer circuits? Buffer circuit is a simple circuit that whatever input you give, the same output we get. Okay. So if your input is high, output will be high. If input is low, output will be low. So basically, buffer circuit is a circuit which replicates the input. Now you might be thinking, sorry, buffer circuit I wrote. This is actually buffer gate. In analog, this is amplifier. Good. Analog electronics, this is amplifier. But in digital, this is buffer gate. So buffer gate, later on we are going to see in combinational and sequential circuit that buffer gate is used for introducing. Can anyone say why is it required? For introducing what? Anyone want to say? for introducing delay. Okay, delay. We are going to study the concept of delay in the next slide. Okay, so basically what? Buffer gate is used for introducing delay. Now let us see what is this delay. So delay, also known as propagation delay. So propagation delay is the time which a logic gate takes to reflect the change in input at the output of the logic gate. So this I have written. If you don't understand the statement, it's okay. Let me explain it to you people. Suppose I have what? I have a NOT gate. Okay. Now to this NOT gate, I apply input. So this is 0, this is A actually. At t equal to 0, input changes from 0 to 1. So ideally, if this is your ideal NOT gate, what will happen? See, output is always complemented or opposite of the input. So output will be something like this. At t equal to, see, if input makes a transition from 0 to 1 at t equal to 0, then your output should make transition from 1 to 0 at t equal to 0 if this is ideal NOT gate. But what happens? Any electrical circuit, it has what? It has by default some delay. Now the delay might be in the range of microsecond to millisecond or even nanoseconds. In modern day computer, the delay is in the form of nano or even picoseconds also. Okay, picosecond. Microsecond means what? Minus 10 to the power 6. Millisecond means what? 10 to the power minus 3. Nano means 10 to the power minus 9. Pico means 10 to the power minus 12. So modern day computer, like the ones we are using right now, it has delays in the range of 10 to the power minus 12. So what happens? There is some delay. So due to that, what happens? Your output, it will not transition exactly at t equal to 0, but at some time. So this I am denoting by, okay, so I have written B over here, sorry. So this will be X. So let me denote this by X dash. X dash indicates this is your delayed output. So this part was t equal to 0. Now you can see your output has basically made transition after del t time or delta t PD. So this delta t PD is basically what? It is the propagation delay of this NOT gate. Tell me if this is clear or not, the concept of propagation delay. So we are going to use this. Yeah, you can also say memory element kind of buffer gate. Tell me, any issues, anyone? Okay, fine. So now let me ask you if you can analyze this circuit or not. So these are NOT gate. I want you to tell me what is this actually, if you have seen this. So this is a very important concept, I will say. So here all the NOT gate have propagation delay del t. All the NOT gates have propagation delay of del t. So tell me now, what will be the output or what is this circuit known as? Think about it. I am giving you like 10 to 15 seconds to think about this circuit. So think about this circuit. So you can start either with 0 or 1. Whichever way you want to start, you can start. What is this circuit? This is feedback. Okay, so I will only say, okay, so you people might not be knowing. So let me tell you. Assume I switch on this circuit and initially the state was 0. Okay, at the input of this, logic gate it was 0. So after del t time, this will be 1. See very carefully. This will be 1 after del t time. Now this one, it will again convert to 0 after 2 del t time, because del t already over here. Then one more del t. So in total 2 del t. And this 0 will be converted to 1 after 3 del t, because already 2 del t up to this point. Then one more del t. So 3 del t. So this 0 is getting converted to 1 after 3 del t. So look very carefully. This is output. Okay, this is your output. And this is also output. So this 0 is getting converted to 1 after 3 del t. So 3 del t. Now look, this one, it is feedback. So it will come back over here. Now look very carefully. This one will be converted to 0 after del t. This 0 will be converted to 1 after 2 del t. And this one will be converted to 0 after 3 del t. Means this one has this one has converted to 0 after 3 del t. Means your waveform will look like this. Okay, so after 3 del t time, this one has converted to 0. Now look again, this 0 is feedback over here. This 0 will be converted to 1, 1 to 0, again to 1 after 3 del t, and this cycle will keep on going. Okay, what is this now? What is this waveform? What is this waveform? What is this waveform? Frequency divider circuit. Yes, you can say, very good. Frequency divider circuit. But here one thing is that actually you cannot exactly say that this is frequency divider. Okay, you cannot say frequency. Why I will say? Because you will have a constant frequency for this circuit. For this particular circuit, the frequency will be what? Frequency, it will be 1 by time period. So this is the time period of the circuit or the waveform, sorry. So that is what? 3 del t plus 3 del t, that is 6 del t, or 2 into 3 del t. Okay, so this circuit, it is known as square wave generator. Okay, or in analog term, means one more term is known as clock generator. Okay, clock generator, or this is also known as ring oscillator. So this we are going to study in sequential circuit. So frequency is given by 1 divided by 2 into 3 del t, or generalized way of telling, it will be what? Frequency is equal to 1 by 2 into n into del t, where n is what? N is number of NOT gate, and del t is what? Del t is propagation delay. Okay, del t is propagation delay of each of the NOT gates. Okay, any doubts? Any doubt? So if you can see, if del t is in the range of microseconds, if del t is in the range of microsecond, frequency will be in the range of megahertz. Okay, if del t is in the range of nanoseconds, this will be in the range of gigahertz. Okay, gigahertz. You can see this is very high frequency circuit. Okay, very high frequency circuit. So number of operations will be also more when you have very less delay time. Okay, any doubts? Anyone want to ask something? Okay, fine. So next, let me ask you, what will be the frequency of this circuit? Please tell me. So if all the logic gate have del t as propagation delay, what will be your this thing? What? This frequency of the circuit. Tell me very quickly. Think very quickly. One by 8. C. Okay. So let me start analyzing the circuit. Look very carefully. This is very important. Let me start analyzing the circuit with 0. So after del t seconds, this will be 1. After 2 del t, here it will be 0. After 3 del t, this will be 1. After 4 del t, this is 0. Now 0, it is remaining 0, or you can see there is no change. So this 0 will be feedback over here and the same thing will continue. And even if you start the circuit from 1, if you assume the circuit starts from 1, so this will be 0, this will be 1, this will be 0. Again you can see this is 1. So 1 will be feedback. There is no transition. There is no transition in the output. So is this a square wave generator or a ring oscillator? Can you see any kind of oscillations in the output? Can you see any oscillations in the output? Like the previous case here, there was oscillations. But here you can see there is no oscillations because your output is not changing. So is this a square wave generator? Tell me yes or no very quickly. No. So then what is the condition for such kind of circuit to be a square wave generator? Note, the condition is that number of NOT gates should be always odd. Okay, always odd. If this kind of circuit has to behave like square wave generator or ring oscillator, number of NOT gates should always be odd. Okay, it should be always odd. This is not clock generator, okay, or even your square wave generator. This is just kind of a buffer. Okay, this is kind of a buffer. Means see, if you apply 1, this output will be 1 after what? After 4 del t. Okay, whatever is your input, same will be the output just after certain amount of delay. So this is actually what? This is your kind of a buffer circuit. Okay, this is kind of a buffer circuit. Any doubts? Any doubts, anyone? Any doubts, anyone? You want to ask anything? Okay, so now then let us move to your NAND gate. Okay, NAND gate. So now NAND gate is what? It is basically your universal gate. Now why is it called universal gate? We will see. Now the symbolic representation of NAND gate, sorry, this I was drawing NOR gate. So NAND gate is basically what? AND gate plus NOT gate. Plus means not addition, means it is combination of AND gate as well as your NOT gate. Or if I want to draw the symbolic representation, it is something like this. Okay, there is a bubble. This is a bubble. Okay, bubble means what? It is basically indicating that it is getting complemented. Okay, so now if I want to draw, first let me write the logical expression. So it will be what? Here it will be A into B. Now if A into B passes through this NOT gate, it will be what? AB complement. So basically X is what? It is AB complement. So this is the logical expression of your NAND gate. Now if I want to draw the universal truth table for NAND gate, so this is low, 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 high. So you can see what, if you ask me that what is basically NAND gate, so if you draw, so you can see what, this low into low, if I AND it, so this will be low only. So when I complement, it will be high. This will be also high. This will be also high, and this will be low. Okay. So basically, if you have to define NAND gate is a gate which is low, which has output low when all the inputs are high. You can see, if any one of the input is low, output will be high. You can see over here, if any one of the input is low, output is high. For the output to be low, all the input should be high. Are you understanding this? If I want to draw the generalized truth table, so I will do something over here also. So very quickly, if you do A complement B, okay, so this will be what? This will be 1, 1, 0. Okay, so this is what? This is your NAND operation. Now one more thing, if you see, if I want to simply do what? A complement or B complement. Okay, A complement or B complement. So 1 or 1, it will be 1. 1 or 0, it will be still 1. 0 or 1, it will be 1. 0 or 0, this will be 0. Now you can see one thing. Look at these two columns. A NAND B is equal to A complement or B complement. Now this is one very important conclusion. Can anyone tell me what is this? What is this? What is this? No, it is not duality law. It is not duality law. De Morgan, very good. So it is De Morgan rule. Okay, it is De Morgan rule. You can see A dot B complement is equal to A complement plus B complement. Okay, okay, fine. So this is what? This is your NAND gate. Now why is NAND gate known as universal gate? Okay, why is NAND gate called as universal gate? So what did I tell you? OR gate, NOT gate and AND gate. With the help of these gate, I can basically do what? I can construct any Boolean algebra. Any Boolean algebra. Okay, any Boolean algebra. Now, if I am able to construct this 3 gate with the help of NAND gate, then I can construct any Boolean algebra with only a single kind of gate, that is your NAND gate. So let us see one by one. If you want NOT gate with the help of NAND gate, so how are you going to do? So I have shorted both the inputs. So if this is A, this will be A, this will be also A. So this will be A dot A bar. So this will be A bar. Now again, if I pass through one more, sorry, so I shouldn't have done this. So here only you can see this is what? This is your NOT gate. Okay, this is your NOT gate. Now if you want to construct AND gate, AND gate. So that will be what? This is A, this is B, this is A dot B whole complement. Now simply if I pass it through a NOT gate, I will be getting AB. Now I want to ask you, can you design this OR gate? Very quickly do. All of you do. Very quickly. See, for OR gate, this is A, this is A bar, this is B, this is B bar. Now if I take these two inputs and pass it from here, so this is what? This is A bar, this is B bar. So this will be A bar dot B bar whole complement. Now just now we have seen that A dot B means this is actually equal to what? A dot B, this is equal to A bar plus B bar. So even this I can write it like this only, where A corresponds to A complement and B corresponds to B complement. So this will be what? A double complement plus B double complement. So that will be A plus B. Okay? A plus B. So this is what? This is OR gate. You can see for construction of NOT, I require one NAND gate. For construction of AND, we require 2. For construction of OR, we require 3 NAND gates. Okay? Is this clear? Is this clear? Okay. So one thing I want to tell you people, see, for such kind of structure, AB plus CD, okay, for such kind of, how many of you are left? Only 4 people. Okay. So after this concept, we are going to wind up the session. Sir, just 1 minute, sir. So with this kind of structure, how many NAND gates do we require? So this is very important. Look, so for constructing such kind of structure, we are going to require so this will be what? AB complement dot CD complement whole complement. Or if you solve this, here if you consider AB complement whole as A, and means this is, I am just telling, let me consider it as X, and CD complement as Y, then this is again in the form of X dot Y, which I can write as X bar plus Y bar. So this will again become what? AB plus CD. So for constructing such kind of structure, we always require 3 NAND gate. And if you see this A plus B, this was OR. So I could have written this A plus B as A dot A plus B dot B. Okay. And you can see for construction of this, we require 3 NAND gates. Even I will give you one homework. Okay. So with this, we are going to end the session. So few homework. A plus BC, how many NAND gate are you going to require? Second, for AB plus CD plus EF, how many NAND gate are you going to require? Okay, so this I want you to solve at your home. So this will be your homework. Okay, so with this I will end the session. So hopefully I am very much hopeful that you have enjoyed the session. Okay, and if there is any queries, you can let me know, or even Dinesh sir is present, you can let him know. Okay,